So welcome, folks. We're just waiting for everybody to come in here, and we'll get things underway. Give it another minute or so here. So one of our panelists has just joined us. Tom, can you just unmute yourself and just talk? We'll just make sure your audio is okay.
Here I am.
Yeah, your audio is good. Thank you. Okay, we're gonna give it one more minute. We'll get things underway. Okay, Chris, let's move to the first slide or to the next slide. So welcome, folks, to our October meet or our September meeting. I'm a whole month ahead of myself here. We're recording this webinar, and for Q&A, please use the Q&A button, not the chat box. Just a reminder that the chat box comments can be seen by everyone, and raise your hand is disabled. So if you have a question for us, please use the Q&A box. The RASC Ottawa Centre acknowledges the trust placed in us by our First Nations with their ancestral lands and sky. So here's the order of things for tonight. We've got the introduction, the Ottawa skies, solar eclipse planning, Bob Olson on Joseph von Fraunhofer. We have a break, and then we have Simon finally back for a great talk on Venus. We have observation reports, some monthly observation challenges, and I believe we may have some members in the news as well. So welcome to our new members. We have 9 new members this month, and welcome, folks. And 63 new members in 2023. This is great. So we have members in the news. We have Oscar and Andrea. Let's see what we have here. So the folks are busy at Starfest, which was a few weeks ago, and they had the imaging competition, and our folks did pretty well. First place ASL. Now, I'm not sure what, I don't know my acronyms. What's ASL?
Astro, Sky, and Landscape category.
Okay, so congratulations to Andrea, first place with her images there. Second place, solar system, Andrea, for our pictures of the comet and the sun and Jupiter. So congratulations. And Oscar was the top 30% for deep sky objects. So he's got, and Andrea was there as well. And the winner of the time lapse was Andrea. Andrea just took all the awards this year. Congratulations, Andrea.
And to top it off,
Imager of the Year. There we go. Absolutely amazing and well-deserved. So congratulations. So I believe maybe one of the 2 of these images might be in the upcoming calendar. We'll talk about that in a little bit. And here are some of the awards, some of the bling that Andrea brought home. Congratulations. So if you'd like to join the Royal Astronomical Society, regular membership is $103. Family membership is $97.50 plus $16.90 an adult, $9.20 per youth. And if you're a student under 21 years old, or if you're under 25 and still a student, $62.40 a year. So what do you get with your membership? Well, as locally, we have our observatory, Fred Lawson Observatory out near Almont. This is a private observatory that's open only to our members. We also have the Ted Bean Loan Library, so if you'd like to borrow a telescope, you're welcome to do that. As we move back to the Canadian Aviation and Space Museum, we'll have access to the Stan Mott Book Library. So we're looking forward to that. We will be moving back to in-person meetings in November, finally. Nationally, you will get the journal and you'll get the Observer's Handbook. And locally, we have the monthly Astronotes published by Gordon Webster. But the best membership benefit is all the people that you meet. All of us come from a wide variety of different backgrounds and experiences. And I find the people at the RASC is the best benefit from being a member here. Excuse me. Okay, Oscar.
Yes, of course. So I've been working to organize the annual dinner meeting for this year. It's going to be taking place Friday, November 24th at Algonquin College. I'm not sure whether it's going to be Solane or not, so those details are still forthcoming. So it'll be 6 p.m. cocktails, 7 p.m. dinner. Admission will be $65 each. I have a speaker mostly lined up. Don't want to say too much just in case, just so I don't jinx myself, but pretty excited about the potential speaker. So I was hoping to get details worked out with them today, but we're still sort of chatting. So once I have that confirmed, I'll announce the speaker. But yeah, it's going to be a great evening. Algonquin has always served us a great dinner. And it's always a fun evening to get together with all your colleagues at the RASC and then get to meet a few new people as well. So if you have any questions, feel free to send me an email, vice-president@ottawa.rasc.ca. I sent an email out yesterday, I believe, with a link to a survey. I'm just trying to get a sense for our numbers so that I can let Algonquin know what to expect. Yeah. So I hope we can make it happen, and it'll be fun to get back together after 3 years apart.
Yes, thank you very much. Yeah, it's an excellent dinner. I've been many times, and I look forward to that. Chris, do you want to speak to the calendars then?
Okay, in the normal way we do things each year, the center is going to do a bulk order of calendars and make them available at a discounted price from the single price that you would pay if you ordered it from the national office. Shortly, I'll be sending out an email to the membership where you can order, commit to one of them. And then once they arrive, we'll have 4 places in Ottawa where you can go to pick them up. Or a new option this year is that you'll be able to pick them up in person at the dinner meeting or at the November or December meetings. But we have only ordered a certain number. We don't order excess. So if you, I wouldn't wait for the meeting to buy it then. You can just pick it up then if you, but if you want to commit to it, you'll see an email from me shortly with the details.
Yeah, we placed a preliminary order today based upon previous year's numbers. So yeah, get your orders in soon. Thank you, Chris. Okay, Ottawa skies for September. Let's see what's going on here. We're already partway into September, but September 15th is the new moon. September 29th is a full moon and a super moon. And this full moon was known by the early Native American tribes as the corn moon, because corn is harvested around this time of year. This moon is also known as the harvest moon. The harvest moon is the full moon that occurs closest to the September equinox each year, and it's the last of the 4 supermoons that we'll see this year. We have the Draconids meteor shower, October 8th and 9th, and that's actually tonight. So it's a minor meteor shower producing about 10 meteors per hour, and it's on the evening of the 8th and 9th. The best time is probably after midnight, and hopefully we'll have clear skies for that. Don't think they're too clear right now, though. Oh, sorry, that's October 8th and 9th. The reason I'm mentioning it now is because of our our next meeting is October 13th because of Thanksgiving. So, okay, sorry, I'm getting my months confused here. As you can see, the days are getting shorter and shorter. So what? Mercury, we have the greatest western elongation. That's where it's the furthest away from the sun. And this is where you look at for Mercury above the horizon in the morning sky on the morning of September the 22nd. And you'll be able to see it either side of September 22nd as well, but this is the best time. Venus is visible before sunrise. Mars is visible in the early evening for the first half of the month. By the end of the month, it's setting too early. Jupiter is visible in the evening and through the night. Saturn's visible in the evening through the whole month. Uranus is visible in the evening through the night. And Neptune's visible in the evening through the night, and it's September 19th. It will be at opposition. And here is our cartoon of the month. There you go. Bit of a groaner, a dad joke, I think. Okay, so we're going to turn it over to Andrea, and she's going to take control here.
Yes, just give me a moment. I'm going to share a screen from my iPad. So hopefully this works. I need to share my screen from here. So I'm going to talk, and I have a certain amount of time to talk about photography, about eclipse planning. But as you know, I do photography. So this focus of this will be on eclipse photography. And can you see the screen?
Yes.
All right. So this is my iPad. And the reason I'm sharing my iPad is, well, twofold. One of the very best eclipse planning tools I have come across lately has been an ebook. And it's sitting on my iPad as an ebook. And it's Alan Dyer's Solar Eclipse electronic book. You can get it in an Apple format or in, I think, just electronic PDF. I highly recommend it because it covers all of the eclipses that are coming up. And he's allowed me to show a few pages here to entice you all to get it because it's very comprehensive. And I think it's maybe $15 US. You can get it from his website, which is down, you can see here at the bottom, amazingsky.com. I'll just give you a quick look at this, and then I'm going to show a couple of apps that I use for eclipse planning. So as you can see here, these are the chapters. Not only does he talk about the annular eclipse, which is happening October 14th, 2023, he'll also cover all the details about shooting the total eclipse in April. And he will also tell you that this book is about photography. It's not about visual. It is basically all the different kinds of eclipse photography. And one of the things I like about it is he talks about wide angle, sort of, as you can see behind me, an eclipse and a foreground, sort of different compositions. He talks actually about shooting time lapses, planning, and then he has an extensive chapter on processing eclipse images. This is an example of one of the many maps that he has. And as you can see, there's the 2023 annular solar eclipse going along one side of the United States, and then we see the map, the path of the total solar eclipse. Now, you might be wondering why today I'm going to talk a little bit about the annular eclipse. We can actually see it in Ottawa. It just won't be a total annularity. It'll be not even as much as this eclipse, which was June 2021. But technically, you can still see the annular eclipse here in Ottawa. An annular eclipse, what is the most important thing to remember is it does not totally cover the solar disk. That means it remains dangerous to your eyes and to your cameras the entire time. So you will need to use solar filters if you're looking at it, and you'll need solar filters if you are going to take images of it. And I'm just going to pop to some of the other parts of this book. So he will talk about specifically the annular eclipse, the total eclipse. He will talk about different photo techniques. I mean, and he'll cover everything: wide angle, stills, composites, smartphones, how to run 3 different cameras at once. He has a section on automation, if you want to automate some of your imaging. It's really an amazing book, and I highly recommend it. One of the things that I'm going to talk a bit about today is planning for wide angle images, because if you're trying to take a picture of the eclipse through a telescope, you're probably only going to have a picture of the sun, and you'll be tracking it on an equatorial mount. To do an eclipse with a landscape like you see here is going to take a different kind of planning. And this is one of the images that he has in his book, and he has several ones. And you can see he maps out the path of the eclipse, and he plans for the different frames for different, whether you have a wide angle lens, a 50 millimeter lens, full frame, or a crop sensor camera. And these details will vary depending on your location. So I'm not sure how much more I need to say about this. I will say that there is an extensive section as well on using Photoshop to process your images. And particularly when it comes to the total eclipse, you will want to, as you can see below here, take different kinds of bracketed exposures and eventually blend them for a very detailed and layered view of the corona of the sun. This book will tell you how to do all that. So I don't have time to say much more about this, except if you want to take a picture during an eclipse, you should get this book and you should read it. So I'm now going to go to, there are 2 apps that almost everybody who does landscape photography with the sky, they use to plan. It is PhotoPills, which is this one up here, and Planet Pro. I'm going to look briefly at PhotoPills, but then I'm going to spend more time on Planet Pro because it's the one that I prefer for a reason that I'm going to show you, which is pretty significant difference between PhotoPills and Planet Pro. All right, so I'm not going to lie, when you first open PhotoPills, it's complicated. There's a lot happening, but essentially where the little red pin is your location where you want to take your photo. And I have this one centered on Albuquerque because I personally will be going to Albuquerque for this eclipse. I'm just going to make sure I already see. If I press down in here is a timeline with a date and time, and I can see that we have the correct date, but we don't quite have the right time. So I'm going to use my finger because it's an iPad. And you can see where I need to go during the day. Here we go. All right, so this will be your sun moving along. Up and down this side is where you have a lot of information in PhotoPills. So your sun is activated. Now I have the sun and the moon, yellow and blue, and you should be able to see these lines moving. This is the path. What I really like PhotoPills for is this little bit at the bottom, and I'm going to go right to the bottom, and you'll see, here we go. Do you see the yellow disc down here? So first you have to load the eclipse. So I'll click over here and I'll load an eclipse. I've loaded the solar eclipse of October 14. Watch this little yellow box here. It's going to recreate what, in fact, you will see at that point in Albuquerque. Oh, I'm going to try to get it to stop. Right, there we go. And you have your exact time. So right here, 11:13 a.m., 12:34. These are the exact times, which actually, another interesting thing is that I think this time is Ottawa time, because I've already planned it for Albuquerque, and in Albuquerque it's 9 a.m. when the eclipse starts. So first off, we have to figure out what time zone we're in, but normally it sets it up for the time zone where you are. In Albuquerque, in Ottawa, this is what the time will be, but we are 2 hours difference. All right, so let me zoom in here. So basically you can zoom in with your iPad and you can move your pin to the exact location where you are planning on standing. PhotoPills will then, this black little thing here, this is the field of view of your camera. And up here, you will see, and actually you can't see, I don't know if you can see it, hang on. I'm gonna move this over here. Up here, you can see there's a D7000, that's the camera. Here you have the lens, and here you have landscape or portrait mode for your camera. So you can put all the information you need, and it will do a recreation, but I'm not going to show you the recreation in PhotoPills because I don't like it. I'm going to show it to you in Planet Pro. I use PhotoPills a lot for the Milky Way. It has a where is it now? It has a, oh yeah, down along the bottom, night AR, and it'll recreate the Milky Way for you in like virtual reality. So I really like PhotoPills for the Milky Way. I don't really like it that much for the eclipse planning. But if you like to do moon alignments, I use PhotoPills to plan the moon rising behind the Parliament buildings. It's incredibly accurate. People who plan images of the sun, of the moon, right on top of the CN Tower, they use PhotoPills. It's an incredible program. But for this eclipse, and I'm just checking my time, yeah, I'm going to go to a similar but different app. This is PhotoPills. I got to go to Planet Pro. You can see it up here. I want to say there might be a paid component to that app. PhotoPills is free. But I got to show you, Planet Pro is so cool. Well, here we go. One of the things that you will realize when you start doing some planning for this eclipse is that it's pretty high in the sky in Ontario for both the annular eclipse and the total eclipse. So if you want to have a foreground, you need to carefully plan where you're going to be and what kind of foreground you have. So what you do when you're in, so once again, I am in Albuquerque. And I press the hamburger menu and I go to something, there's photography tools, ephemeris feature. I'm going to select Eclipse. And you can see up here, I have the annular solar eclipse and it shows the time. It's going to start at 9:13 a.m. The full will start at 10:34. These are all my timings. So I've got exact timing for this location. And down along the bottom here, this is your timeline. It's also a timeline that you can move. And you see my sun and moon moving around there? That's how you plan. So we know that the sun and moon will be to the south of us. And this green line, I'm pointing to the wrong thing, this thing here, this is your focal, this is your camera. This is a wide angle camera. Eee, that's a telephoto lens. So I was going to start by showing you the virtual reality. I'm going to show it with a zoom lens, just so you can get a better, so you can see the sun, because otherwise it gets really small. So here we go. On this side, once you've found a location and you got the right time and we've planned everything, you can go to Viewfinder VR over here. All right. Now I should be able to find the sun here somewhere. All right, I don't see it. This is where the live part is hard. Okay, I'm gonna go there. Oh, and I might have to go to photography tools and I might do panorama. All right, let's see what I see now. Come on. Oh. So up here, you'll see I have a 200mm lens, landscape, and my total field of view is not very big. I'm going to change that. I'm going to see if I can get it bigger. Let's see, 60. Set. All right. Oh, there it is. All right. Now you can see them. There it is. I'm going to reduce that to 20. Set. I don't know, you can't see it too well, but this, as you can see, as we move the timeline, we are able to see the sun and the moon. But this is not what I'm going to do with Planet Pro. I want to plan a wide field view. So I'm going to look at, I'm going to probably do a 35mm lens. I'm going to have it in portrait mode. And whoop, there's the ground. You see, there's the ground. Planet Pro will download actual mountain elevation, which PhotoPills cannot do. All right, so let's go down to the beginning. All right, see, I can have my images start. See, there's the sun and the moon over here. And over time, and I can plan, okay, I can almost get, I can't quite get the whole eclipse in there, but I can get part of it. Oops, where'd you go? There you are. This, most of the eclipse happens really high. So one of my thoughts is that, and I'm going to go back to the map, I need a foreground. I need a really high foreground so that my high moon and sun, so I have something. So I'm going to get really close to this mountain. I'm going to move my camera, woo, right up to the mountain. Now look at what happens when I use the virtual reality. There's the actual mountain. So Planet Pro can download precise elevations with mountains. And look at that. I can almost get the whole eclipse into this frame. Now, to be clear, this actually is not just one 35mm lens. If you look along the bottom here, you see these green lines? These green lines is a panorama planning tool. What I actually have is three images. So I have to do take my images of the sun, and as it starts to move out, I have to rotate once, and then I'll have to rotate a third time. But I should be able to, with 3 images in portrait mode, again, I'm here, the camera's up and down. I should be able to get the whole eclipse in with proper planning and with a foreground. And that's nice because they can help sort of orient the wide field. Otherwise, a wide field image doesn't look so great. I could try, this is your field. I could try going to like 45 to see if I could do it in maybe 2. Okay, so down here, we now only have 2, a panorama of 2 images. And let's see, I might be able to fit the whole eclipse in. Look at that, that's not bad. And I just discovered this new feature. It's even better. Hang on a second. I'm probably running out of time now, but this is a really wonderful planning tool, particularly where there's mountains. When I was out west in the Rocky Mountains, I use this all the time because you think you have a really good view of something and there's a mountain in the way. Okay, so I'll just show you one last thing, which was, this is an ephemeris feature sequence. Look at this, a sun sequence. So let's go back to the planner, to the virtual. You can see it actually maps out the eclipse path for you and says, if you look up here, you need to start at 8 a.m. You're taking 29 photos and it's going to end at 12:57. So maybe you could automate this. I don't know if I would, but it's a wonderful way to plan not only your framing, but whether you want to be in portrait, landscape mode, whether you need, you're going to need a tripod, but you don't need a tracker for this. You're not moving your camera other than maybe moving it once. So that's going to be my plan for Albuquerque. You might not be going to Albuquerque and you want to just stay in Ottawa. So I can come back to this, but I want to just go to PhotoPills and just show you what's going to happen in Ottawa, because that's important to know too. So I'm going to take my pin. I'm going to, oh, hang on. Oh, stop. Take my pin. I'm going to drag it over to Ottawa. There we are. Ottawa. I'm going to zoom in. And once again, I need you to look at the little sun down here. I'm not quite in Ottawa. I'm somewhere, somewhere in Mont-Tremblant. Okay, here we go. Now I'm in Ottawa. Watch this little square here, and I will move the timeline. So we get a little tiny bit of eclipse up here. And you can see the actual times are visible here at the bottom. 12:05 to 2:23. So if you have safety goggles, you will need them for this. If you know people who want to go and watch this eclipse, you can use photo pills to find the exact times. And I didn't want to say, I have a whole bunch of these. They've been branded for my law firm, but I was going to donate a whole bunch of them to the Ottawa group here. And so if you would like to get some, if you're a member and you would like to get some glasses for you and your family, give my office a call. I'll throw my email in here somewhere, and you can come pick them up, because I am donating them to our membership. And I wanted to let people know now, because there aren't any more meetings until you get really close to the eclipse. So that's all I have to say about these apps. If you have questions, you can certainly email me. Oh, that's my timer telling me that's 20 minutes. Look at me, I'm right on time. I'm going to stop sharing, and I'll take questions if there are any about that. I know it's a lot of information. I'm sorry.
Andrea, maybe I'll start with the first question.
Okay.
Could I ask you in the chat group to post the name of Alan Dyer's book and maybe a link where people can get it?
I will. Yes.
Maybe while you're at it, just repeat the names of Photo Pills and Planet Pro.
I will. I will do all those things. So, oh, I can send to everybody. Certainly, I will do that. Are there any questions?
I don't see any at this time, but if you do have some questions, Andrea can answer them offline through the Q&A box. So
That's
thank you very
amazing.
much.
Right.
That's very good. I've downloaded the book, purchased and downloaded the book myself.
Okay,
Excellent
great.
resource. Okay, we're going to turn it over to Bob Olson here. Let me, there we go.
Maybe before you start, there's actually a question already from Mick about what types of filters to use.
Are you talking about on the camera, or I'm assuming that's what he's talking about? Yes.
I mean, all I can say is that the book will talk about all the different kinds. I actually meant to bring, when I do my observations, I actually made a homemade filter for all my cameras, and I'll show it. But Alan Dyer's book also talks about all the different kinds of filters for photographic use. And I do know that what you use for a camera is not necessarily what you would use for your eyes. So you do have to be careful. The eyes need a lot more protection than your camera.
Okay. Chris, you're in presenter's mode or something with the slides there. We're seeing the current slide and next slide. So we'll try that again.
Okay, bear with me.
And we're now seeing Bob full screen. There we go.
Does that look better?
That's much better. Thank you. Okay, Bob. So he's got us. Wants to tell us about this fellow named Joe. What can you tell us about Joe?
Okay, there we go. I have known the name Joseph von Fraunhofer since the start of my teaching career in 1970. When I gave my RASC presentation on Bunsen and Kirchhoff, Fraunhofer's name kept coming up in ways that I did not expect. It was obvious that I knew next to nothing about Fraunhofer. Time to hit the books. Next slide. The dark lines on this spectrum are called the Fraunhofer lines. This is part of every physics class from high school on. This spectrum was drawn by Fraunhofer. It is the spectrum of the sun. The black lines make no sense at all, as it is a black body which should produce a continuous spectrum. Don't you love the fact that the sun is used as an example of black body radiation? It turns out that the black lines are the colors of light that have been absorbed out of the spectrum by the sun's atmosphere. This allows us to know what the chemicals make up the atmosphere of the sun. This also works for the stars. This is not a photograph, but a drawing. The precision of this drawing is a great demonstration of Fraunhofer's technical expertise. Next slide, please. I do not know the geography of Germany, so I need to look at the map. The 4 cities underlined in red are the significant locations in the life of Fraunhofer. He was born in 1787 in the town of Straubing. He was the 11th child of Franz and Anna. For several generations, the Fraunhofers had been window glaziers. In 1799, when he was 12, both his parents died. He was then sent as an apprentice to Munich, where he worked for a mirror maker. He had a great desire for education, but his master saw no point in it. This caused friction between Fraunhofer and his master. The other 2 cities are Erlanger, where you will find the University of Erlangen, and this is where Fraunhofer was awarded a PhD, and where he served as a professor. And Benediktbern, where Fraunhofer worked at the glass foundry. Next slide, please. 2 years later, in 1801, his master's house collapsed on Fraunhofer. Apparently, mirror makers are not great carpenters. Like today, there is no news better than a disaster. There was widespread interest in this collapse, and the rescue was led by Prince Elector Maximilian IV. That's him in the middle of the picture. The prince was so impressed by Fraunhofer's talents that he supplied him with textbooks on optics and mathematics. The prince also gave Fraunhofer a financial donation toward his studies. Although this collapse was a big boost to Fraunhofer, the lady of the house did not survive. Next slide, please. The fame Fraunhofer achieved by being buried alive also brought him into contact with his future employer and partner, Joseph von Utzschneider. Utzschneider did encourage Fraunhofer's master to allow his apprentice to study. Utzschneider had previously been a privy councillor in the prince's administration and was a wealthy businessman. Next slide. In 1805, Utzschneider bought the Benediktbern Abbey from the crown. What, might you ask, was the crown doing with an abbey? It turns out that in 1803, 2 years earlier, the crown had secularized all the monasteries. They then sold the land and buildings to whomever would buy them. At the time it was secularized, the abbey had a library of 40,000 books. Some of these went to the Munich libraries, some were disposed of by the owners, and some were used to level cart paths. His plan was to build a factory to produce glass and the instruments that you could make from glass. To do this, he would need a smart, young, and ambitious man. Any idea whose name came to his mind? Next slide, please. In 1806, Utzschneider offered Fraunhofer a job. Next slide, please. Although Fraunhofer was smart, he didn't know much about smelting glass. So Pierre-Louis Guignard was also hired. Pierre was a Swiss glassmaker. If you want to make precision optical instruments, you need to first have high quality glass. Utzschneider planned on doing both. Next slide, please. One of the innovations that Pierre came up with was a method to stir the glass as it was being melted. This produced much better glass. If you look closely at the drawing, you can see a stir crank at the top. How would you like the job of stirring molten glass a few meters above a blast furnace? Being young and smart, Fraunhofer had lots of ideas about the production of glass, but Pierre kept the recipes and methods used to produce the glass a secret. Finally, Utzschneider ordered Pierre to share his knowledge with Fraunhofer. Next slide, please. In 1811, when he was 24 years old, Fraunhofer was given supervisory responsibilities for the entire operation, including the production of the glass. He was also made a partner in the Optical Institute. Soon after this, Pierre Guignard, the Swiss glassmaker, left the company, taking all the glassmaking secrets with him. Utzschneider tried to bind him to the company by offering him a pension, but this trick did not work. This meant that the competitors now had the recipes and methods to make their own glass. Several areas in Germany did develop into significant producers of optical glass. Next slide, please. This painting shows Fraunhofer in his workshop. He improved the quality of the glass being manufactured, which allowed him to produce better and better optical instruments. In 1818, the abbey and the surrounding land was sold back to the crown. Utzschneider only kept the glassworks. In 1819, the Optical Institute, which manufactures the optical instruments, moved back to Munich. This meant that Fraunhofer needed to travel between Benedikta-Barn to make glass and Munich to make the instruments. Next slide. Even if you can make good lenses, you still need to put them in something. So besides the optics, you need good mechanicals. This is a gear cutting machine, as Fraunhofer would have needed accurately cut gears for many of his optical instruments. This machine looks rather lightweight, but in actuality, it weighed over 1,000 pounds. Next slide, please. Fraunhofer was German, and many of the articles I read about him had been translated from German. I assume that most of these articles were written by historians rather than scientists. They appeared to sometimes confuse the words dispersion, diffraction, and refraction. This made reading parts of the article somewhat confusing, but I eventually learned to substitute the correct word on the fly. This was important as Fraunhofer was involved in all of these. So what are dispersion, diffraction, and refraction, and why are they important? Refraction is the bending of light when it changes medium, say from glass to air or air to glass. Dispersion describes the fact that different colors of light refract different amounts. As you can see, red light bends less than violet or blue. This is important if you want to make lenses, because lenses will also split white light into colors. This would give you a terrible image. Diffraction is defined as the bending of light around corners such that it spreads out and illuminates areas where a shadow is expected. I will come back to diffraction later in the presentation. Next slide, please. Almost 150 years earlier, in the 1600s, Sir Isaac Newton was also experimenting with prisms, splitting white light into colors. He stated that the amount of dispersion, that is the splitting of white light into colors, was exactly proportional to the refractive index of the glass used to make the prism. If this were true, it would be impossible to make a lens or a lens system that did not split light into colors. One of Newton's less attractive personality traits was the fact that he viciously attacked anyone who disagreed with him. For almost 100 years, scientists were afraid to question Newton's thesis on the connection between refraction and dispersion. Next slide, please. When light travels through a glass lens, the lens acts like a skinny prism and splits the white light into its component colors. This is because blue light bends more in glass than does red. You can see the star focused by this lens is a blurred and colored mess. Next slide, please. In 1733, 54 years before Fraunhofer was born, George Bass combined lenses made from different types of glass, one lens being convex and the other concave. He found this combination did not flare out the colors as much. The story of George Bass's discovery is convoluted and slightly crooked. A man called Chester Hall came up with the idea of combining flint and crown glass to make a color-free lens, but he wanted to keep it a secret, so he contracted the making of the flint glass lens to one optician and the crown glass lens to another. But both these opticians were busy or lazy, so they subcontracted their lens to George Bass. So poor old Chester's idea for secrecy didn't work so well. George Bass immediately realized these two lenses were for the same customer. When he put them together, he noticed they did correct for color aberrations. He made a telescope using his stolen idea, but it never gained much traction. He eventually shared the idea with John Dollard. Next slide, please. In 1758, 29 years before Fraunhofer was born, John Dollard used his twice-stolen idea to make a similar lens combination using crown glass and flint glass, which corrected the colors well. This was the first production achromatic lens. He had the nerve to patent the idea. In 1765, 22 years before Fraunhofer was born, Peter Dollard, John's son, made a lens system with 3 lenses, which corrected the colors even better. We call this level of color correction apochromatic lens. In today's refractor telescopes, triplet lenses made from exotic types of glass are the gold standard in telescopes. Next slide, please. If this knowledge had been around for 50 years, why do we give Fraunhofer so much credit for developing refractor telescopes? Because he studied the optics of different colors of light and different types of glass. He made all of his measurements using very precise instruments of his own design and manufacture. He then calculated what these lenses should look like and made them to his calculations. Previous lens makers used trial and error rather than design. For example, he measured how much each color would bend through different types of glass and accurately measured that bend. Here are some of his colored prisms that he used in his experiments. And of course, he had good glass. The earlier opticians were hampered by very bad glass. It was not consistent. Even a single lens would vary, and the glass would have bubbles and bits of debris in it. Fraunhofer made his own glass, which was much superior to any glass before. Next slide, please. This is a diagram of Fraunhofer's achromatic lens design. The crown glass is made from silica sand, alkaline salts, and lime. The flint glass is made from silica sand, alkaline salts, and lead. If you think these ingredients heated to 1300 degrees would be dangerous, you might be right. The furnaces were heated using wood and could barely reach the 1300 degrees Celsius. Today's glass is melted at 1500 degrees, so getting a good mix at 200 degrees cooler was quite a chore. Next slide, please. This is one of the glass furnaces at the Abbey. The place certainly has the air of a blacksmith shop. I must make it clear, this was not a one-man show. At its peak, Fraunhofer oversaw 48 employees, varying between glassmakers and lens grinders. In the period between 1811 and 1825, they produced 6,000 kilograms of precision glass. So what did Fraunhofer and his employees produce with that 6,000 kilograms of glass? Next slide. Fraunhofer was not the first person to think of an achromatic lens, but everyone else was trying to solve the problem by trial and error. Fraunhofer was making measurements of the properties of glass and designing his optics accordingly. This telescope has a 9-inch diameter lens and was built by the Deutsche Museum using Fraunhofer's plans. So it is a replica of one of his scopes. Fraunhofer was able to build lenses with apertures past 25 centimeters. That's 1 foot, which had been considered impossible up until then. He even produced a 49 centimeter lens for the Russian Imperial Observatory. Next slide, please. This is another example of Fraunhofer's telescope. Besides how pretty it is, I'm fascinated by the intricate drive mechanism. This telescope, as does my own, is sitting on a German equatorial mount invented by none other than Joseph von Fraunhofer. It can accurately track the stars across the skies as the Earth rotates. Next slide, please. More Fraunhofer telescopes. He was a major world supplier of scopes. A telescope made by Fraunhofer was used in 1846 to discover Neptune. Next slide. And microscopes. Fraunhofer was the first person to see the relationship between the resolution of a microscope and the wavelength of light. 25. Next slide, please. This interesting gizmo is a heliostat. It would be set in a sunbeam as the sun traversed across the sky. It would move and direct the beam into your stationary apparatus, say a telescope or a spectroscope. Next slide, please. This is a theodolite. It's a precision instrument used for the measuring of angles, both horizontally and vertically. Theodolites can rotate along their horizontal axis as well as their vertical axis. This is an example where the mechanical part of the mechanism is equally important as the optical. Next slide, please. And of course, he made spectroscopes. Next slide. In this painting, Fraunhofer is demonstrating a spectroscope to a group that includes the owner of the business and his benefactor, Joseph Utzschneider. Utzschneider is on the left, and Fraunhofer is wearing the dark jacket. Next. This is just a quick reminder of the optics of it in a spectroscope. The collimator is a lens or series of lenses that makes the light beam coming from the slit in front of the light source into a parallel beam. This beam is sent through the prism where it is split into the colors. The resulting color bands are observed by a movable telescope. This telescope has an accurate scale to show its position. This allows very accurate measurements to be made of the spectrum. Next slide, please. Now we get back to diffraction. Fraunhofer, when looking through a single slit, saw a pattern much as you see on the screen. He experimented with different widths of slits and found that a narrow slit spread the light wider. He also noticed the black bands on the single slit pattern and concluded that light must be a wave. These black bands were produced by the interference of light passing through different parts of the slit. The image from these single slits is very dim, so he figured that he would use a double slit to make the image brighter. But instead, he found the more interference bands were being produced. When he experimented, he found that the closer the slits produced wider interference bands. And again, this made sense if light was a wave. He constructed multi-slit diffraction gratings using strands of wire. But eventually he used a diamond to scribe lines on a piece of glass, and the spacing was only 3.3 microns. That's how far apart they were. Using these diffraction gratings, he was able to accurately calculate the wavelength of light going through his spectroscopes. His results deviate only by parts per thousand of those measured using modern instruments. Using the wave theory of light, Fraunhofer was able to derive a diffraction grating equation that is still in use today. Next slide. Sadly, in the year 1826, Joseph von Fraunhofer died of lung tuberculosis. It is widely assumed that the toxic environment around the blast furnaces contributed to his early death at the age of 39. His gravestone reads, "He brought us closer to the stars." Next slide. What is Fraunhofer's legacy? From the Fraunhofer lines in the sun spectrum to the first production modern telescopes, Fraunhofer changed the way we look at the sky. His scientific achievements are incredible, but he was also a clever businessman. He introduced entirely new methods of developing and manufacturing industrial products. He did this systematically and without preconceived ideas. The manufacturing The manufacturer now had complete control over quality, yield, time, and cost. It was an entirely new way of thinking. Next slide. He has buildings named after him. Next slide. He has a statue. Next slide. But in this modern age, here's the most astonishing example of all. Using artificial intelligence, he has been brought to life as a digital avatar, the highest honor that we can bestow on a person in 2023. Thank you. Have a great day.
Thank you very much, Bob. I have one question here. Well, actually, it's a comment from Mick Wilson. You're so good at this history stuff, Bob. Why do you think Fraunhofer is only associated with spectra, more or less?
I think he's well known in Germany. All the stuff I found on him was basically German translations. I'm a scientist and I'm supposed to know about these guys. I didn't know any of this stuff before I started looking into it. No idea.
Okay, thank you.
Yeah,
Yeah, fascinating. Thank you very much, Bob.
you're welcome.
Okay. So we have some open positions at the RASC as we move into the new year. We're currently looking for a meeting chair. We need a national representative. Somebody who looks after hospitality as we move back into our in-person meetings. We used to have some folks who would look after the coffee and cookies and so on. We'd like somebody to step up for that position. And Andrea's had to step down from the light pollution abatement position. So we're looking for somebody to replace that. If you're interested in any of those positions or need more details, please email myself, president@ottawa.rasc.ca, and I'd be happy to fill you in on the requirements for those jobs. And we're hoping to get all these locked down for our December meeting, so that we go into the new year with a full slate of positions filled. We have some outreach opportunities, and this is where we'd love to get some of your help. On Friday, September the 29th, so it's just coming up in a little bit here, the Pathfinders, these are Girl Guides ages 12 to 14 years old. They're having a large gathering, 300 of them, at the Apple Hill Scout Preserve. It's sort of near Alexandria in that area. They got a marvelous large field, dark skies, and we'd love to get a bunch of folks there with their telescopes to help us out. This is the date they picked. Unfortunately, it's the full moon, super moon, so a lot of things are going to be washed out. But certainly being able to look at the moon through a telescope, or even some other things pointing away from the moon, would be awesome. So if you're interested, please email outreach@ottawa.rasc.ca. Folks who attend this must pre-register because we need to send you a code of conduct form to bring with you because it is Girl Guides. Okay, so we also would like to know how many people we have to support us there. I've been doing a session with the Ottawa Public Library Rockcliffe branch, and I'm doing a presentation in early October for the adults. I've already done one for the young kids. And what we'd like to do is get our telescopes out on Monday, October the 16th at 8 o'clock with a rain date on the Wednesday. And it's in the Rockcliffe Dog Park. It's a massive park, sort of near the parkway, and good view of the southern sky. And we don't know how many people are going to turn out to it, but it will be heavily promoted by the public library. So we'd love to be able to support them. Again, please email outreach@ottawa.rasc.ca if you can assist with either one of these. We really appreciate it. Thank you. Okay, so we're going to take a 5-minute bio break. And question is, where is the coldest place in the universe? So we'll see you folks in 5 minutes.
So you can see me, you can hear me.
Yes, absolutely.
Excellent. All right. So Venus is very much in the forefront of interest and excitement in planetary science these days. It's as though it's gone from being the poor relation with respect to, say, the Moon and Mars, to being the place everyone wants to get on board with, sort of the new planetary El Dorado. So tonight I thought I'd take a look at why this is so, why all the recent and current excitement. If you aren't already aware of just how much excitement Venus is currently generating, look at this compilation of multi-billion-dollar missions already financially approved by 4 national and international space agencies with launch dates spread over the next 10 years. It's true that the Veritas mission, the funding has been suspended for now, but now note that they're not expected to send back any new data from Venus until the mid-2030s. Whatever, these will be the first wave of missions planned to look at all aspects of Venus since NASA's Magellan mission of the early 1900s. Sorry, yes, the early 1990s. 1900s would be a little early. Now, I know some of you are aware of some of the media headliners relating to Venus because I've told you about some of them last year already. There was the Life on Venus story, driven by the phosphine molecule in the Venusian atmosphere. And the twin notions of both tectonic activity here and volcanism on Venus that might be very recent and perhaps even happening today. I also briefly mentioned this keynote idea. By modeling the evolution of the atmosphere of Venus through time, it's possible to develop a climate scenario where, for about 3 billion years, early Venus may have been cool and wet, even with an ocean, and potentially habitable until an outpouring of huge volumes of lava sometime during the past 1 billion years resurfaced much of the planet and turned it into the dry hothouse that it is today, with surface temperatures in excess of about 450 degrees centigrade. That resurfacing would happen right there, and that's when the heating would have occurred. However, this is just one model. Folks are still asking the question, when did Venus heat up, or was it always hot? Now, an important consequence of Venus being hot and dry is that there has been very little surface erosion during at least the past 500 million to 1 billion years or so. Winds at the surface are not very strong, which means that what we see at the surface pretty much formed at the surface. And as we'll see, this has major repercussions for when we make comparisons with the Earth. Now, I think it's pretty obvious that before spending huge sums of money on science missions, we should have a pretty good idea of what we already know and do not know about the place that we're sending these expensive missions to. You have to know what the next questions are to ask. Now, this is fundamental to any science project if you want to get the maximum value for the effort and funds expended, especially when we're talking billions of taxpayers' dollars, which have to be justified. So let's do a whistle-stop tour of what planetary scientists think they know already about the surface of Venus, and what they think they need to know more about, hence these missions. Then for the rest of the talk, we'll look at what I think they don't know, even though they think they do, if you're following me. Now, I'll keep this first part very brief because I've already gone over some of this in some detail with you back in 2020. Oh, and by the way, all the images of Venus that I will show you are radar images because they were taken looking through very thick clouds of mostly carbon dioxide. Now, first, we know that 80% of the surface of Venus, and this, by the way, is a map of the whole of Venus, ironed out onto a rectangular shape. We know that 80% of the surface of Venus is made of volcanic plains, and they're in the dark gray that you can see in this image, most of the image, in fact. So much of it is relatively flat. The other 20% includes relatively high-standing plateaus. That's the medium to light gray stuff. So this kind of stuff here, 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 and here, over here, and up in there. And some planetary scientists compare these plateaus with what they think terrestrial continents might have looked like on early Earth. Another major feature of Venus is a connected network of huge rift valleys. That would be these light gray strands out through here, for example. There are others up here, and up through there. Think Ottawa Valley, or better still, think of the East African Rift as terrestrial analogs. And these rifts, they occur where the planetary crust was pulled apart, probably by tectonic movements in the planetary mantle. Volcanoes, particularly shown here well in the white, here and here. They're present in all shapes and sizes, and some of them are actually as big as plateaus. And then there are large, by large I mean 100 to 500 kilometer diameter, round dome-like features, giant ones up here, but there are many others all over. At this scale, they're rather difficult to see, but you can see some of them here and here and here. These are referred to on Venus as coronae, and they're very common in the volcanic plains. They're thought to form as mantle upwellings that reach the planetary surface and then collapse to form raised rings. Now, the principal arguments advanced by the planetary science community for a massive return to Venus fall basically into three categories. Climate change. Planet may be changing from cool and wet to now dry and hot. How did it happen? Does that have application to Earth? Exoplanets around other stars. How to avoid confusing an exoplanet, an exovenus, for an exo-Earth around a star somewhere outside of our solar system. And better resolution for geological mapping. However, the large-scale geological features in our whistle-stop tour, a whistle-stop overview, some of which are rather complicated, are actually reasonably well resolved in the existing Magellan radar data from the early 1990s. So as you can imagine, they've been extensively studied and are pretty well understood within the limits of the data resolution. And yet, these are the very geological features that most folks seem to want to remap using these expensive new missions. It's ironic because it's the simple basic stuff that I suggest currently defies understanding. And by basic, I mean structures formed by simple pushing, simple pulling, or simple sideways sliding. Nothing very complicated. So let's start by looking at a simple basic structure that formed in response to rocks being pushed, or shortened, as they say technically, on Venus. They're called wrinkle ridges. Now, both of these busy images here, each about 100 kilometers or more across, of the volcanic plains of Venus show lots and lots of features, but I want to zero in on the long, thin lines. They're like this, in this image, they even go across like this. They're even in a sort of a rectangular network over here, and they swing across through here. Pretty busy stuff. These are what are referred to on Venus as wrinkle ridges. I don't expect you to see much here, but this is about as good as it gets in terms of resolution. To see better, we have to turn to the original wrinkle ridges first described on the Moon. No surprise, they're closer and easier to see. They're long, hundreds of kilometers in length. They're sinuous, they wiggle, and they're high-standing ridges made of a broad rise with a wrinkle on top of the rise. So here's a cross-section, a broad rise with a wrinkle on top, another broad rise with a wrinkle on top, and so on. Well, here's the broad rise, and this here would be the wrinkle on top. Their most characteristic feature is that they're mostly asymmetrical, with a steep slope and a shallow slope. So here's the shallow slope, and there's the steep slope. Steep slope, shallow slope. Steep slope, shallow slope. It's all over the place. And here we see the lunar example that I just showed you on the left, and one of the best images of wrinkle ridges from Venus on the right. The scales are different, but you can see why planetary scientists use the lunar examples as analogs to help interpret ridges on Venus. So why are wrinkle ridges so important on Venus? Well, Venus has more wrinkle ridges than any other planetary body in the solar system. The planet scale map on the right, that's the whole planet, shown as a rectangle. And the detailed blow up on the left, which is essentially the red box, gives you an idea of just how widespread these wrinkle ridges are. They're difficult to see here, but the gray areas are actually made of lines, as you can see here in the detailed image. You can also see how they occur as multiple vast fields of evenly spaced periodic ridges. That's the individual lines, extending for well over 1,000 kilometers, both along their trends and across them, throughout the volcanic plains of the entire planet. There are few enough places that you don't see them. They're such a characteristic feature of Venus that we really do need to understand how they formed. Now notice something very important about the detailed map over here, especially this area down here. The wrinkle ridges are drawn as simple lines, just simple lines. Keep this in mind because I'll come back to it shortly. It's very important. Now this is the classical consensus cross-sectional model, cross-section, for how wrinkle ridges are thought to form. Very similar to the racking up of a carpet that slides over a rigid floor. This dark line here, by the way, is the surface of the planet. And then you're looking at, maybe a couple of kilometers down in depth here. In the model, the topographical relief of the ridges is due to folding of the upper layers of the volcanic plains. You can see the fold here and here and here. The periodic or even spacing of the ridges is due to the folds occurring in trains. And that's just a characteristic feature of folding everywhere. And according to the model, the asymmetry of the ridges, in other words, the shallow slope here and the steep slope here, that's due to the formation of a fault, which you can see in the red here, 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 that forms beneath the growing fold and drives the formation of the fold itself. Now note that the red fault, does not break the surface. Hence it's termed blind or buried. We cannot see the fault, and therein lies the first major problem. Now, as I pointed out in a science paper I published earlier this year, it turns out that this model is not a unique explanation for the formation of periodic asymmetrical ridges. Compare the shapes progressively produced through time, 1, 2, 3, 1, 2, 3, 4, through time, produced with a fault that cuts across the layers, that's the red here cutting across the layers, with one that slips along the layers, that's this red line here. The shapes of the ridges are very similar as seen from above, as you would actually be looking from a telescope, from a satellite in orbit. This means that the classical wrinkle ridge model is what's known as a non-unique solution. And therein lies the second major problem. Worse, the distribution of wrinkle ridges in vast uniform fields, measuring thousands of kilometers in every direction, presents a structural geological conundrum. Let me show you why it's a major problem. The Rocky Mountains of Western Canada, that's this area here, is the Rocky Mountains. They're built of slabs of rock separated by faults that slid over one another about 40 million years ago. That's shown in a cross-section going from west to east. And although the faults, which are between the slabs of rock here, they look like they're evenly spaced, the two red arrows, this one here and that one there, they are actually marking a master fault between the arrows, along which much of the crustal contraction or shortening was taken up. The fact is that nature doesn't like to spread work out evenly. If there's a way to get the work localized onto one weak surface, nature will take it. Geologically, this is called the localization of deformation. Remember that word, localization. And it's a fundamental principle of the deformation of rocks anywhere. Yet it appears to be absent from these vast fields of wrinkle ridges on Venus. They're uniformly spaced. And this is a third major problem that's so far been ignored in planetary geology. Now, on the topic of what's been ignored, you may be surprised to learn that we have practically no data regarding the shape of wrinkle ridges on Venus, which would be diagnostic, if we had it, for the mechanisms that might have formed them. Despite the fact that there are lots of geological maps on Venus, the wrinkle ridges on all of the maps are presented as simple lines, as I've shown you, with no information regarding the sense of ridge asymmetry, if any, and therefore no diagnostic information regarding mechanisms of how these wrinkle ridges formed. In other words, the all-important diagnostic wrinkle ridge shape or asymmetry on Venus is an assumption. So what now? Well, the good news is that Venus offers planetary scientists a chance of a lifetime, an entire planet absolutely riddled with wrinkle ridges, and all they have to do is determine if the ridges are systematically asymmetrical or not. Do they all have an asymmetry pointing the same way? It's a pretty simple question with a yes or no answer. In the simplistic case where most of the ridges turned out to be symmetrical, there might be no requirement for faults at all, and thereby no requirement for the localization of the deformation of the volcanic plains. Well, so much for basic structures related to pushing. Now, what about simple pulling? Well, for this, I'll focus on what are called the rift fabrics of the crustal plateaus that stand proud of the volcanic plains. Now, these crustal plateaus, they have names here. I won't worry about the names, but they're here, here, and here. Here's a big one. There's another big one up here. And there's a nice big one down here. Those are the principal ones. And those are the things that we're going to be looking at. Now, here on the lower left is a satellite's view of a large chunk of a plateau with hundreds to thousands of long linear features oriented north-south. They look like scratch marks in this picture. They go from here to about there. They're oriented north-south. They're uniformly developed, over 500 kilometers along and 1,000 kilometers or more across their overall trend at the scale of the plateau. This is only a part of the plateau, by the way. Now, for reasons I won't get into here, we know that these are very long, narrow rifts, so close-spaced that folks talk about a rift fabric. That's what they call a rift fabric, these beautifully uniformly spaced rifts. And this is, of course, is a blow-up of this. The scale bar here is about 12 kilometers. That distance is about 500. Now, let's see where yes, there are two ways to generate this rift fabric, either by stretching the crust in response to externally imposed forces, or by internally inflating, like a balloon, if you like, the planetary crust. The consensus view is that the Venusian crust has been stretched. The minority view, including me, is that it has been inflated. So let me explain. At upper left, that's this stuff up here. At upper left is an inset with the two consensus models for creating these long, skinny rifts by tectonically stretching the crust, essentially by pulling it apart by forces outside of the crust. The details here do not matter. The major problem here is similar to one of the major problems with wrinkle ridges, but much worse. If you pull rocks apart by external forces, they do not break like this. One or another of the initial rifts is going to grow faster than all the others and turn into a major localized, there's that word again, localized rift as nature tries to economize the work done to achieve the overall stretching. True, we've already seen that major planet scale rifts do occur on Venus, but they have nothing to do with the rift fabrics. There's something altogether different and very well understood. So what's the alternative? Well, in a science paper published back in 2020, I suggested that the Venusian rift fabrics might be the product of inflating the crust from within. How? To answer that question, we have to ask another. Do we see similar, extensive, periodically spaced linear features elsewhere in the solar system? And well, yes, we do. On Earth, we find the remains of giant dike swarms throughout geological time and all over the planet. These are massive swarms of narrow vertical sheets of molten rock, magma, that individually can be thousands of kilometers long. On the left, that's this here. On the left, you see an example from northern Canada, and the inset to the on the right of that image there is a detailed line drawing of what part of the swarm looks like close up. That's this thing here. On the right of the image, you see a radar image of the a rift fabric from Venus and a detailed line drawing of that radar image. This and this, this and this do look pretty similar, even if the scales are different. So before we go any further with this, what exactly are magmatic dikes and what do they look like on Earth? On the right of this slide, you can see a swarm of black sheets cutting across a very large outcrop in southwest Greenland. This was hot liquid magma that forced its way into the surrounding rocks and pushed them apart to make room for the pressure of them, to make room thanks to the pressure of the magma itself. That's these black things here. These are the dikes, and there's a huge one going across like that. In short, the dikes inflated the crust into which they were intruded. They inflated it by their magmatic pressure. To the lower left, you can see similar dikes cutting across a flat plain in northwestern Canada. Are there other examples? Well, if we look at a digital elevation map of the area north of the Tharsis uplift and Olympus Mons on Mars, that's the colored figure to the left, we can see a very similar map scale pattern of very thin, very long, evenly close spaced rifts extending over thousands of kilometers in all directions. They are essentially oriented north-south. The surface images on the right are details of Tractus catena. Tractus catena is shown here in this block, where you can see pit chains within the rifts that many planetary scientists, that's these things here, and those things there, and these here. Those pit chains, which many scientists interpret as collapse pits, indicating the presence of the tops of dikes that lie just below the surface under the rifts. Okay, but I still haven't explained what giant dike swarms might have to do with vast swarms of long, narrow rifts, especially if the dikes are still buried just below the planetary surface. So without getting into the details, it turns out that when a pressurized magmatic dike, in other words, the dike is under pressure, rises to near the surface, it generates a stress field that pulls the surface apart and pushes the surface rocks up on either side to form a rift, a long, skinny rift valley called a graben. So since we observe examples of very long, close-spaced features related to underground sheets of intruded magma that inflate the planetary crust over vast areas measured in thousands of kilometers in every direction on both Earth and Mars, my question was this: does the same process apply to the rift fabrics of Venus? Remember, this is a hypothesis on my part. I don't know the answer yet, but I will. Okay. So we've looked now at simple basic structures related to pushing and pulling, or possibly crustal inflation. What about structures related to simple sideways sliding on the surface of Venus? Well, there's no denying that vast volcanic plains of Venus, on Venus, are indeed divided into large, undeformed blocks, which are dark gray, separated by zones of deformation in the light gray. You can see them here. These are the dark gray blocks, separated by light gray belts, if you like, which are areas of deformation. And this is a close-up on a larger block, and these are the deformation zones surrounding it. And we can refer to these colloquially as rigid lumps, separated by squishy zones. We don't need to get technical here. However, some planetary scientists claim that the squishy zones are corridors of sideways slip, technically referred to as shear zones that would allow the rigid blocks to jostle around and slide past each other in a manner analogous to blocks of terrestrial sea ice. So these would be the blocks, and these light belts here would be the squishy zones where things are jostling. They also suggest that this represents both a form of plate tectonics and what our planet might have looked like before modern plate tectonics got established here on Earth. In addition, they suggest that this sideways slipping might be happening on Venus today, hence the notion of currently active tectonics on the second planet. If correct, This would be revolutionary. However, there are several major problems with this idea. First major problem, if we zoom in a little on the previous slide so that we can read the scale bar, we can see, there's the scale bar, that's 0 to 250, 500 kilometers. Each one of these divisions here is 50 kilometers. If we zoom in, we can see that the squishy zones, that's these here and here, they're well over 100 kilometers wide. Remember, there's been very little erosion on Venus for at least the past 500 million to 1 billion years. So how could huge sideways slipping shear zones be active at the surface of the planet, of any planet? I'll come back to this in a second. Second major problem. Planetary scientists are not in agreement as to why they think sideways slip is even present on Venus. Their analyses are universally model dependent. Here on the left, in a published analysis of a purported shear zone on Venus, that's supposedly all these lines here. Note the scale bar. The proposed shear zone is 50 to over 100 kilometers wide, depending on where you measure it. The arrows on either side of the shear zone, that's these arrows here, they're indicating which way the blocks of crust moved across the shear zone. And in this interpretation, they indicate that the blocks moved this way and that way. This is called left-handed. In other words, as you look across the shear zone, the other block moves to your left. That was a mistake. Let me go back one. There we go. So that shear zone interpretation is left-handed, but on the right is a blow-up of the same shear zone. That's in fact the red box here in the really wide part. And it's interpreted by a different group of planetary scientists as right lateral. Look, compare that arrow with that arrow and that arrow with that arrow. They're opposite, and it's the same supposed shear zone. So without getting into detail here, if you don't know which way a sideways slipping shear zone slipped, then you really don't know if it's a shear zone at all. I spent a major part of my 40-year career as a geologist, actually it's now getting on for 50 years, at studying sideways slipping giant shear zones in northern Canada, especially at Grey Slave Lake in the Northwest Territories. Great Slave Lake is here, and the Great Slave Lake shear zone is this red thing, and I studied this part of it. Actually, I discovered it. On the right, in the line drawing, is a simplification of my detailed map of the Great Slave Lake shear zone that formed about 2 billion years ago. And it was, and it still is, the widest sideways slip shear zone known in the history of the Earth. Note the scale bar here. The shear zone is a maximum of 25 kilometers wide. Terrestrial shear zones cannot be wider than 25 kilometers wide. But why? The different patterns in the Great Slave Lake shear zone map represent rocks deformed at different temperatures and different depths within the Earth's crust. The shear zone was 25 kilometers wide when the rocks we see at the surface today were located at about 35 to 40 kilometers depth within the crust at temperatures of 850 to 1,000 degrees centigrade. While the shear zone was active, the hot rocks were progressively unroofed, exposed. By erosion, they rose towards the surface and cooled to about 450 degrees centigrade at about 10 kilometers depth. Remember that temperature. I'm going to come back to it very soon. The rocks deformed at those cooler temperatures cut through the once hotter rocks and are indicated on the map by narrow black units. That's this here, and this one here, and that one up there. They're called green schist myelinite. Don't worry about them. The important thing is they're only about 1 kilometer wide. So what's the link between hot rocks and wide shear zones? Well, a shear zone forms where Mother Nature wants to localize, there's that word again, localize the slip between two large blocks into a narrow corridor, do less work. And shearing can do this, sideways slipping, because the very act of deforming the rock in a shear zone grinding the rocks down, if you like. It's actually more complicated than that, but don't worry. Grinding them down makes them inherently weaker. So you get a feedback. The more deformation, the weaker the shear zone, and the narrower the zone of deformation. This is called a mechanical weakening process. However, at high temperatures, rocks are inherently weaker too. Think of the difference between brittle taffy at room temperature and soft taffy when it's heated in a saucepan. It's a very similar phenomenon. If the rocks are already at 1,000 degrees centigrade, in other words, almost ready to melt, which is as weak as rocks can get, then there's not much advantage to further mechanical weakening, is there? So hot shear zones are wide because the rocks are thermally weakened. 25 kilometers is the maximum width because any more heating will simply melt the rocks, and they can't get any weaker than that. But when you cool the rocks to 450 degrees centigrade, mechanical weakening becomes dominant over thermal weakening, and the shear zone narrows, it localizes, that word, towards a stable width of just 1 kilometer. So there are just two things to remember here. First, 450 degrees centigrade is the approximate temperature of the Venusian surface today. And second, structures seen at the surface of Venus must have formed pretty much at the surface because erosion is so weak. Oh, and by the way, squishy shear zones do not form at all at very shallow depths. Instead, they form brittle faults, which are between 1 and 100 meters wide. In short, the supposed side-slip shear zones reported by planetary scientists from Venus do not seem to correspond at all to what we know about sideways slipping shear zones on Earth, especially if they formed at the surface. So we have to ask ourselves, are they even shear zones? And if they're not, then what are they? In truth, I don't know. We may have to wait for the new data in the mid-2030s. So, okay, how do we wrap this up? As I said at the beginning of this talk, planetary scientists have a good grasp on the often complex, broad-scale aspects of the structure of the crust of Venus and of the volcanology that built it. They even have a reasonable grasp of the planetary atmosphere. However, planetary scientists have not done such a good job with the simple basics of the structural geology of the Venusian surface. They still cannot adequately justify their interpretations of the relatively simple processes of pushing, pulling, and maybe the sideways sliding of rocks. Unfortunately, they do not appear to realize this. In other words, they do not know what they do not know. And I fear it will show up in their detailed mission plans for further geological mapping. So should planetary scientists just sit on their hands waiting for the new data from the Venus missions sometime in the 2030s? I think not. I have two very brief principal suggestions. First, go back to the Magellan mission data from the early 1990s and high-grade the best quality parts. Some of those data are in stereo, but they're very small, like what we call postage stamps, although most are not. Regarding wrinkle ridges, use the best stereo data to test whether or not the wrinkle ridges of Venus really are asymmetrical as is assumed or not. If they're not, this fundamentally opens up the paradigm for their formation to reinterpretation. Regarding the rift fabrics, if they're really formed above blind magmatic dikes, then at least some of those millions of dikes must have leaked to the surface. And we should be looking to see if they have filled the bottoms of any of the rifts. If they haven't, scrap the hypothesis. Second, planetary scientists have ignored terrestrial structural geology for far too long. They should go back to the library and read and learn and better understand the well-established universal laws that govern the behavior of rocks undergoing simple basic deformation. Remember, these are the laws of physics and chemistry, and they apply to all rocks, wherever they're found in the universe. As always, thanks for listening, and I hope to see you all at meetings November and beyond, when we can actually all be there in person. Thank you.
Thank you very much, Mick. That was fascinating. I was thinking during the talk, can you say side slip shear zones 5 times really quickly? Sorry.
I commonly have to do so.
Yes, you handled it very well. Let me just see if there's any questions here. Hang on. Oops, I hit the wrong button. Oh, hang on. Yes, no, that's somebody was just saying it's a fascinating talk. So thank you very much.
Dave, can I just point out that this talk is actually already posted on my website, which you can access via the education button on the RASC Ottawa website.
Okay.
And then go down to planetary geology, and then from there go to presentations, and then go down to Venus. It's number 5 in the list of Venus. If you want to go over all this stuff again with exactly the same illustrations.
Super. Thank you very much. So we're going to move now on to our observations, and Andrea, you are up first. So let me spotlight
Thank you.
you.
Okay, and I'm just going to take a moment just to, I don't know if you can see, this is my homemade solar filter with Bader paper that I use for all my cameras. So it's homemade, very inexpensive. I have a giant roll of it. All right, this is an image of two nebula, dark nebula, known as the Shark Nebula up above, LDN 1235, and there's a little lower nebula with a blue reflection nebula at the end. And there's great debate over what we call this. Some people call it the penguin, some people call it the dark worm. I had a book that called it the Wolf's Cave because it was discovered by somebody called Wolf. In any event, its designation is VDB152. And these are some nebula that can be found in the molecular cloud in Cepheus. This was one of my images from Starfest on the one really, really clear night we had. This was shot with a really wide angle lens, 180 millimeter lens. Oh, and an astronomical camera. I think it was the 2600 MC. And there was actually these objects were so faint that I couldn't see anything on any of the individual images. And the whole night I thought maybe I was pointing in the wrong direction. But it turned out pretty nice. This is about 6 hours worth of images. Next, please. Saturn was at opposition on August 27th, and I tried to do my best to get a picture. It was really, really low. It's really low this year. And I had a filter malfunction. I think I took all my images through the same filter. So here's my black and white image of Saturn at opposition this year. And I didn't get a color one. So that's all I got. Next, please. Right. So this is the sun, what the sun looked like on August 5th. And it's actually a 12-panel mosaic. When I take my images with the quark has a built-in 4x Barlow, which really zooms in. So I actually have to use a reducer to broaden the field of view. And I was quite pleased with this mosaic because I used 2 new and exciting tools in Photoshop called Auto Align, and it automatically aligned all the panels. It was like a miracle. And then it did Auto Blend, and it blended all the mosaic and put everything together. And there you go. It did a pretty good job. So that was our sun on August 5th. Next, please. Okay, so before you press play, Chris, I just want to put some context. The title was actually the Starfest CME. So this was an image that when I was at Starfest, I got up one morning and I was looking at the sun with the Lunt 40 millimeter, my little tiny solar scope. And I could see this huge extended red glowing prominence jumping out of the sun. And actually I screamed and I woke up all my neighbors and they all came and they looked at it. And by the time I got my camera, I only saw a little bit, but you can see on the surface of the sun, there's a really white little circle area. And that was where there was a big solar flare and it launched a giant CME towards Earth. And that was a little bit of it you see there. And at the end of this animation, I went to the J heliosphere place to get actual footage from SDO 304 angstrom footage. So you'll actually see what this giant thing looked like. And you can press play then, Chris. And this is, I had it on my Instagram. It's pretty small. I'm not sure what happened. But keep your eye on the west limb and you'll see that giant thing that's jutting out. Well, that was pretty much what I could see in sort of real time happening when we were at Starfest. And so that was kind of fun and exciting. Next. I think this is my last one. So this is, this actually turned out so much better than I thought. This is a single exposure. It's a 13-second exposure with an Astro modified camera up near Muskoka. And so this is Lake Joe. And it was such a calm night that I actually, not only did I get a reflection of the stars and the star color in the water, I actually, you can see there's some reflection of the core of the Milky Way. So this is what a dark sky can do. You can see the bands of air glow as well. And this just happened to be in the right place in a dark sky. And I took this as a single image. So I was pretty pleased with how this one turned out. That's all for me. Thank you.
Thank you, Andrea. We've got Tom up next.
Click on the button. Yeah, we've seemed to have so few clear nights the last several months. And then when it was clear, we'd have a full moon. So I did some narrowband imaging of the southern portion of the East Veil Nebula. And that's what this is here, using the Hubble SHO palette and PixInsight to put together. This is only about 20 minutes exposure per band, so about 60 minutes total. I've also trying to get the regular LRGB for this, but hopefully get some clear nights without a full moon. And we'll see what comes out of that. I also captured Saturn near opposition there, but it was the last night to submit the images, so I didn't get it put together in time. So maybe I'll put that up next time.
All right. Good evening. So I've got two images to show tonight. The first one is this one here. This is NGC 5033. It's a spiral galaxy in Canis Venatici, about 38 to 60 million light years away. I think, Chris, if you click once, you should zoom in a little on the galaxy. There we go. So this image was taken with an ASI 2400 MC Pro color camera through my 11-inch GHD at f7 on the evenings of April 14th and 15th this year. So it's composed of 204 3-minute sub-exposures for a total integration of 10 hours and 12 minutes. Next one, please. This is the Veil Nebula, which is also known as the Cygnus Loop. It's a large supernova remnant in Cygnus. Its three most well-known components are the Eastern Veil Nebula, which is sort of that crescent-shaped area on the left of the image. The Western Veil Nebula, which is the sort of the arc at the far right with the bright star kind of in the middle of it, which is also known as the Witch's Broom, because it kind of looks like the handle of a broom with the little brushy bits on the bottom. And then Pickering's Triangle, which is at the top near the middle of the image there. So this is a narrowband image at Starfest on the nights of the 16th and 18th of August. And it was using the HOO palette, meaning that hydrogen alpha was mapped to red and oxygen was mapped to both green and blue. So it was taken with an ASI 2600 mm Pro monochrome camera through a Skywatcher Equinox 80 ED. So it's about 4 hours and 5 minutes of H alpha data and 5 hours and 15 minutes of oxygen data. for a total integration of, what is that, 9 hours, 20 minutes, I think is what it adds up to, if my math is right in my head. I think if you click once, I think if we can click through each of the components. Yeah, so this is the Eastern Veil. Once more. That's the Western Veil, so that's the witch's broom. You can kind of see it. You can, if you look at it with the right imagination, it looks like a broom. And then lastly, Pickering's triangle, or Fleming's triangular wisp, as Paul is pointing out. There was an article in Astronomy magazine, I believe, that corrects the name of this particular feature. All right, I think that's it for me. Thank you.
Thank you. So, Rick.
Good evening, everybody. So starting off with an image of Albireo, of course, the colored double star at the head of the Swan Cygnus. This is when I start my evenings observing every night. The first thing I do with the telescope is I slew off to a bright star, just to ensure that the pointing is held good since the last observing session. And since I was out doing outreach for Queen's University and for Parks Canada on 2 evenings in August, and Albireo was one of the most popular targets for all those people, I thought it would be a good one to slew to and check my pointing. And so while I was there, I took 28 5-second exposures with the ZWO ASI 2600 MC Pro camera. And that's on a Meade 25 centimeter f4 Schmid Newtonian. Next, please. So one of the pretty pictures I was trying a month or so ago was M27. This is using the same scope and camera, but with a dual band filter. So it lets through H alpha and O3 light. So red and sort of a blue green. So it should show up. The hydrogen alpha should show up in the red channel, and the O3 should show up in the green and blue channels. And when I stack the images and process the color, this is what I get. It's white with sort of brownish hydrogen alpha features. So many years ago, I had shot M27 using an actual H alpha filter and an O3 filter on a monochrome camera, and I stacked them all together and made what's called an HA0303 image, and it came out quite nice. This was sort of 10 or 15 years before it became somewhat popular to do so. So I attacked this one the same way that I did in the past, and I was not having any luck. Kept getting things that looked like this or that were completely off. So finally, I do all my stacking in a program called Cirrel. And in the latest version of Cirrel, they have a new color balancing tool. If we go to the next slide, you can see it's given us the more traditional, this one I haven't titled up the background and stuff, but this gives us much more akin to what we normally think of for M27. Basically, what this tool does is you tell it an object that's sort of in the center of the frame, and it will actually then plate solve the image. It finds all the stars in the image for which there is photometric data, and then it color balances the image so that all the photometry in the various colors is correct. And basically you just click on the button and it goes, and this is what it came back with. I do kind of like the pale white and sort of orangey colors, but this is a more traditional look, and for regular imaging, this is just a great way to very rapidly color balance your images. Next, please. So this is the supernova SN 2023 IXF that was discovered in M101 on the 19th of May at a magnitude of about 15. Others have already shown pictures, far better pictures of it than this. However, just to point it out, it's the brightest star in the field, basically. That's the one just above center. And so this is 9 20-second exposures with a photometric V filter using the Boltwood 40 centimeter Newtonian. So we aren't able to just take pictures of them. We can actually measure the brightness of the star. So next, we have the my observations. So I imaged it on 13 nights over a month, late May and early June. Started out about 11th magnitude. You can see there's one discrepant measurement there that I have to track down what's wrong with that one. But you can also see, for instance, that around that time I had 7 observing nights in a row, then a gap, and then 4 nights in a row, and finally late June, my last observation before M101 disappears into the trees northwest of my observatory. So what I do is I shoot 10 exposures over the period here. They ranged from 20 seconds to I think about 60 on the last night. And I do photometry on all 10 images. I take an average of the result, and that can give me an error estimate. And then I submit these to the AAVSO's, the American Association of Variable Star Observers international database for other people to use. And interestingly, every weekend, they send me an email saying how many of my observations and of what targets have been downloaded and what purpose they were downloaded for. And of course, being a bright supernova, this one's getting downloaded a lot. Let's see. Archival, well, let's go to the next slide. So here I've compressed the scale, pushed all my observations up into the top left corner, because you would think a bright supernova like this would, I mean, there should be a fair number of people interested in observing it. And next slide, you can see that there are, in fact, 212 people who have been interested in observing it, 14,502 times as of a few minutes ago. Most of these observations are done with CCD cameras, or more commonly now CMOS cameras, but a lot of them are using DSLRs or one-shot color cameras. And there's actually even about, I think, 400 observations done visually. Since it was as bright as 11th magnitude, it's quite easy to track visually. So what we're seeing here is the black triangles on the top are infrared observations. The red triangles